Welcome to our astronomy course on stellar physics. Today we build a complete, step-by-step guide to reading the Hertzsprung-Russell diagram, the map of stellar life. Before the details, here are 4 headline facts. It was developed between 1911 and 1913. The spectral classes are O, B, A, F, G, K, M. About 90% of stars lie on the main sequence, and luminosity spans 10 orders of magnitude. Step 1 is historical background. Hertzsprung noticed that stars of the same spectral type can have very different luminosities, which hinted at giants and dwarfs. Russell then plotted spectral type versus absolute magnitude for many stars and showed a clear pattern. By 1914, the astronomy community recognized both contributions, and later Eddington and Payne provided the theory. Luminosity relates to mass, and stars are mostly hydrogen. Step 2 is reading the axes. The horizontal axis is temperature and spectral type. Temperature increases from right to left, which is reversed from most graphs. The vertical axis is luminosity, increasing upward on a logarithmic scale. This diagram also encodes radius because luminosity depends on radius and temperature. Step 3 is spectral classification, from hottest to coolest. O, B, A, F, G, K, M. O and B stars are blue, white, and very luminous. A and F are white to yellow. G is yellow like the sun, K is orange, and M is deep red. Spectral lines reveal composition and temperature. Step 4 is the main sequence. This is not a time sequence, but a mass sequence. A star is stable when gravity is balanced by pressure from fusion. Low-mass stars fuse by the proton-proton chain. Massive stars use the C and O cycle. Luminosity scales roughly as mass to the 3.5 power, and lifetime scales roughly as mass to the negative 2.5 power. That is why massive stars are bright but short-lived. Now let's locate key regions on the HR diagram. The main sequence runs diagonally from hot luminous stars on the left to cool dim stars on the right. Giants are upper right, and white dwarfs are lower left. Steps 5 through 7 show how stars leave the main sequence. Low and medium mass stars exhaust core hydrogen, ignite shell burning, and expand into red giants. They later enter the asymptotic giant branch, shed their envelopes as planetary nebulae, and end as white dwarfs. Massive stars evolve rapidly into supergiants, build iron cores, and explode as supernovae, leaving neutron stars or black holes. Step 8 covers extreme objects. White dwarfs are Earth-sized and supported by electron degeneracy pressure. Red dwarfs are the most common and live for trillions of years. Neutron stars are tiny, ultra-dense, and can appear as pulsars. Black holes have event horizons and emit no light directly. Step 9 is the mathematical framework. The Stefan-Boltzmann law connects luminosity, radius, and temperature. The distance modulus connects apparent and absolute magnitude to distance. The mass-luminosity relation explains the main sequence slope, and bolometric correction accounts for light outside the visible band. Step 10 is spectroscopic parallax. We read spectral type and luminosity class, infer absolute magnitude from the HR diagram, measure apparent magnitude, and compute distance. Step 11 is cluster age dating. The main sequence turnoff point gives the cluster age because massive stars evolve first. Step 12 is stellar populations. Population 1 stars are metal-rich and younger, found in the galactic disk. Population 2 stars are metal-poor and older, found in the halo and globular clusters. Population 3 are the first stars, hypothetical and metal-free. Step 13 is variable stars in the instability strip. Cepheids are supergiants with a period luminosity relation used for distance. RR Lyrae are standard candles for globular clusters. Delta Scuti stars probe interiors, and Mira variables trace late AGB evolution. Summary: the HR diagram maps temperature versus luminosity, encodes radius, and organizes stellar evolution. Most stars sit on the main sequence. Giants and supergiants occupy the upper right, and white dwarfs sit in the lower left. With this diagram, we measure distances, ages, and the life cycles of stars.